So you should have already tried problem 7 all on your own. Let's go through the solution, starting with a good free body diagram. We already see it's moving to the right. And so we'll start with our usual stuff. We know we're going to draw a weight straight down, and it's on a level surface. Normal force is going to point straight up, and it's just moving to the right. There's nothing funny happening here. There's no vertical acceleration. There's no extra vertical forces. In this case, normal force is just going to match the weight. And we know this is a friction force because it says so. And we know friction always opposes motion. So if the object is moving to the right, the friction, of course, is going to point to the left. So we know the weight is 88.2 newtons. Normal force is also 88.2 newtons, and friction is given as 22.5 newtons. So there it is, pointing to the left. And that should be the entire free body diagram. I hope you have nothing else there. You absolutely should not have anything pointing to the right because it doesn't say anything is pushing to the right. You should not make assumptions. It doesn't say anything about that, so we can't just assume that it's moving to the right. There's also a force to the right. There had been a force to the right to get it moving, but in this case, it doesn't say that that force is still being applied. You let it go, and friction is bringing it to rest, so there should be the entire free body diagram. You should not make assumptions. All right, letter B, you want to find how much work each of the forces does. So we're thinking about using F delta X cosine theta. Let's focus on the normal force first, and you're always thinking about what the angle is, and that's why we still draw free body diagrams. It's moving to the right, normal force points straight up. That's an angle of 90 degrees, and cosine 90 at this point we should definitely have under our belts is 0, and so the work done by normal force is 0, OJ. Force of gravity is pointing straight down. It's moving to the right. What angle is that? 90 degrees again. How much work is the gravity force doing? 0, right? They're both doing 0 joules. We've seen this before. Now, that's not always going to be the case because we've seen a problem number 5 where that wasn't the case, but it happens here that anytime they're perpendicular to motion, they're doing no work. Vertical forces should not be able to affect sideways motion. So the only thing doing work here is the force of friction. What angle are we looking at there? Well, it's moving to the right. Friction points to the left. That's an angle of 180 degrees. So we've got force of friction, delta x cosine theta. Force of friction is given. Displacement's given. Here's our cosine of the angle. Now, here's where some students might get a little confused and say, well, wait a second. It's moving to the right and friction points to the left. Should I put in a negative 22.5? No. Notice I haven't even assigned a positive direction here because we're dealing with work and energy and everything's scalar, so we don't have to assign a positive. Plus, since everything is scalar, when you put the numbers into the equation for work, you're only putting in the magnitudes. In this case, the magnitude of the force, the magnitude of the displacement. The sign of the answer, that's going to come here when you put in the proper angle for the cosine theta. So it's just 22.5 times 0.8 times cosine 180, and we should be getting negative 18.0 joules. Let's pause here for a second and remind ourselves, what does it mean if we get negative work? Well, we know negative work happens when the force opposes motion, sure, but remember also work is an exchange of energy. This is saying that the work done by friction is taking 18 joules away from the object. The object is losing 18 joules of energy, negative work being done. All right, letter C, you want to find the net work. Well, it's for sure real easy. We got 0, 0, negative 18. That looks like negative 18 joules to me. And notice that since normal force and force of gravity aren't doing any work, the net work is just the work done by friction. That's not always going to be the case. That's just what happened here. Now I want to find the initial speed. This is what I was saying on Classroom, is that you could do this problem by doing a full free body diagram as we've done, assigning positive direction, doing sigma F equals ma, doing some kinematics, but let's not do that. Let's keep this in the realm of work and energy. So how are we going to get the speed into this? Well, hopefully you remember the big central equation of this topic, that net work equals change in kinetic energy. Right. And we know kinetic energy is linked to speed, so from here, we should be able to find the initial speed. So if you hadn't done that, well, pause the video now and go from here and solve for the initial speed. So we know that change in kinetic energy, a delta, is always final minus initial, KEF minus KE naught. In this case, it was initially moving, so it has initial speed, but it's brought to rest. So in this case, final kinetic energy is going to be 0. And so net work equals the negative of the initial kinetic energy. So it's going to be negative 1/2 mv naught squared. Initial kinetic energy goes with initial speed. And that's what we're solving for. Now the net work, remember, is just the work done by friction, so we already know that. This is great. So we can just rearrange this and solve this for v naughts. Remember, we always want to rearrange the equations first. You know, that's how I've been training you. So in this case, v naught equals negative 2w net over m, take the square root. But wait a second, this is not looking good because we seem to have a negative under the radical. We've talked about this before. That's an impossibility. You can't take the square root of a negative number. Oh, but wait a second. The work done by friction, which is the net work, is a negative number. So we're going to be just fine because this is going to be a negative number. It's going to go in there. It's going to cancel the negative sign. Whew! Everything's going to be just fine. But that's the sort of thing we should always be thinking about. If you ever get an unexpected negative sign, it means something went wrong somewhere. So let's put our numbers in, and let's solve. So we have negative 2 times negative 18 divided by the mass of 9 kilograms. Take the square root, and we should be getting 2 meters per second.